Okay, fantastic. Morning, everyone. The session is being recorded for your information, or just answering some questions. But first of all, let me tell you, I already set a forum on MyWBS on modules webpage for the group assignment. So if you have any queries which is related to the group assignment, not specific to your own group's problems, do essentially post them on the forum so that everyone can see the answer. This is the first thing that I wanted to tell. You will have announcements. Have a look at the announcements, because last week I'm teaching on Wednesday and Fridays, and I don't really have enough time to check my emails. But I was asked some questions that we can simply find the answers based on the assignment announcements. For instance, I was asked what is the time of the drop-in session, but it was already announced. So I won't tell something just verbally to you like this, that I'll have a drop-in session at this time in my office. So it was already announced on modules webpage. Come back to the questions. Where can we see the model answer format for the assignment that you mentioned? Last week in the workshop, we did a transportation problem. It was generic. It wasn't manual. I showed you, I mentioned it a few times, that this is the way that you have to do your group assignment. Essentially, you have to write the models in a way that if I change the data set, if I amend the data set, I have to be able to get the solutions immediately without changing your code. This is what I said. So this is essentially an example that you can find. If you have any questions, as I said, please post them on MyWBS on the forum, which is designed for the group assignment. I will answer it so that everyone can see it. This is the first thing I wanted to say. I will have another drop-in session sometimes next week, hopefully, so that you could pop in and ask your questions related to the group assignment. But be aware that I won't answer specific questions, like if this is this correct? If you ask me, I can answer that. So this is what you have to figure out. But if you have any generic or general queries about the group assignment, you'll pop in and ask your questions, okay? All the questions should be done this way, or just transportation problem? Come on, I'll just answer it. It's just all questions should be that one. What do you mean transportation problems? Transportation problem was an example of generic model code. So all your problems should be written in the way that transportation problem was written, so that I changed the data set from transportation data set to transportation extended, and I didn't need to change the code or the model or anything. This is what I'm saying, okay? That was an example of a generic code. Okay, enough for the group assignment. You can post your questions on the forum. Please just focus on this VIX materials and contents, which are important for the module itself, okay? Please, no more questions about group assignment when I'm teaching. Just focus on the content of this week. Again, because I know some of you will ask questions, do not ask any question on the chat box about the group assignment from now on. Just leave them to the forum, please. Great. So this week we're going to focus on mixed integer linear programming models. You had this objection from the beginning when we started linear programming, that when I told you that the decision variables are continuous, some of you objected, which was a valid objection, that if you're producing cars, for instance, the decision variables cannot be continuous, and it was a valid objection. I told you that, I agree with you. This is something that we will cover on week 6 and 7 this week and next week. Remember that a linear programming, if you go back to the assumptions of linear programming models into the first week, a linear programming model, a model is linear programming if all functions are linear, and then we said that the decision variables should be essentially continuous. Continuous means that they can get any values. It can be 2, it can be 2.1, it can be 2.4, 2.6, whatsoever. So this was essentially one of the assumptions that we had. And on the top of that, we said that for a linear programming model, we have to know everything with certainty. So if there is a price, the price should be fixed. It can be like uncertain. You will see more uncertainty in other modules. We don't cover it now. But next time in AMA, a bit of it might be covered. But going back to the case of linear programming, functions should be linear, which means that unknown or decision variables are only multiplied by the coefficients constants, and then decision variables should be continuous. Now, as I said, there are certain cases, for instance, if you're producing cars, you can produce 2.3 cars. You either produce 2 cars or 3 cars. In these cases, the decision variable is not continuous anymore. Now, this comes to essentially to mixed integer linear or integer linear programming models. So here, so I have a bit of explanation that we have this maximization problem where we have a function here which is let me just turn it on, the laser pointer. Okay, we have a linear model here which is CJ multiplied by XJ. The unknowns are just multiplied by constants. We have constraints here, 2 sets essentially. Some of them are less than or equality, and some of them are equality constraints. So this is basically what we had for the supply constraints in the transportation problem. If you remember, we had summation of the left-hand side. We had summation on one index, and then we had for all constraints for the right-hand side. For instance, the whole thing that factory ABC, which are sending to different distribution centers, should be less than or equal to the supply or capacity of the suppliers, if you remember. Here you can see that we have I, which is the same for the first set and the second set, because what I can get is divided to different parts. So we have from 1 to M, from 1 to K is for the first constraint, for instance. If I can be from 1 to 10, from 1 to 4, it's less than or equality. From 5 to 10, it's equality constraints. And then we have non-negativity constraint here. And remember that by default, if you have non-negativity constraint, this means that essentially we have continuous decision variables. This is basically is the assumption of divisibility. Decision variables are allowed to take fractional values, 5.2, 6.1, half, 0.63, or whatsoever. If you're talking about paint problem, for instance, if you want to produce something which the unit of the decision variables are in terms of tons, you can produce 2.5 tons of paint 1. You can produce 2.3 of paint 2. You can produce 8.775 of paint 1 or 2. So this is the assumption of divisibility. Depending on the nature of the problem, you can assume that the decision variables can take any fractional values. This is something that we do if the nature of the problem, whatever we are working on, allows us to do that. But there are certain cases, as I just mentioned, that we have to have integer values. So remember from Python training workshops that we had different sort of variables. We said integer, numerical variables. Numerical variables, they can take different values, float or real numbers. And on the other hand, we had integer values, 0, 1, 2, 3, 4, 5, 6, whatsoever. There are integer values. Why bother to use integer decision variables? Because the nature of the problem doesn't allow us to have fractional values for the decision variables. If the variable is associated with a physical entity that is indivisible, then it must be integer. Number of airplanes, number of cars, number of laptops to be produced, for instance. You can produce 2.5 cars. You can produce 7.2 laptops. You can produce 10.2 airplanes. It is either 10 or 11, 9, 12, 0, 1, 2, 3. So there are integers. There are other sort of decision variables that we have to decide on whether or not to do something. This is also an integer decision variable. Remember, yes, no, true, false. What do we call such variables? Do you remember from Python training? If you have yes, no, true, false, which sort of variables they are in Python? Boolean, fantastic. Yes, Boolean decision variables, great. they're Boolean decision variables. And Boolean decision variables, there are like two outputs that we have, yes or no, true or false. It's 0, 1, essentially, two integer values. So they're Boolean decision variables. If you want to decide whether or not you want to produce, you have options, alternatives to produce different products. You have to decide which one is the most profitable one. You will decide at the end of the day, are you going to produce product 1 or not, 2 or not, 3 or not, whatsoever? Yes or no, 0 or 1 for each of them. It is an integer decision variable. So it's not essentially linear programming anymore, because the decision variables are not continuous. We call them integer programming or mixed integer linear programs. Still, we have linear programming there at the end because the functions are linear, but decision variables are not continuous anymore. If all decision variables are integer, we call it integer linear programs. If some of them are integer, some of them are continuous, we call them mixed integer linear programs. The main areas in which IP is used in practice, we have a few examples here. We have capital budgeting with investment. You want to decide which investment options to choose. You have a few options: investment 1, 2, 3, 4, 5, 10, or 10, let's say. You want to decide if you invest on any of them. By investing on which of them, you will have the maximum return. Site selection, that's a fantastic problem. Facility location. In industry, it is worked a lot. Last year, I've worked with a company to decide where they have to build their depots. They wanted to decide the warehouses. They had like different options in different cities. They wanted to have the warehouses where more demand can be satisfied with least traveling for the delivery guys, essentially. So we want to decide, there are like options to have the warehouse. They want to decide whether or not they're going to build a warehouse in Coventry, whether or not a warehouse in Kenilworth, whether or not a warehouse in Rugby. So each of them, yes or no, true, false, 0, 1, integer decision variables. Scheduling is another one that we see a lot in reality. We want to assign jobs to the machines so that the objective function is essentially to minimize the total completion time of all jobs. We'll cover one of them in the materials that we have this week. Airline applications, fleet assignment. Essentially here, whether to assign certain types of plane to a given flight leg based on the demand that they have. So there are different sizes of airplanes that exist, big ones, medium ones, small ones, I don't know how they are called. But if you use a massive airplane for a flight leg from city A to city B, that the number of seats are too many compared to the demand of the leg, it's waste of resources. So you want to decide on which planes should be assigned to each, to which flight legs of this specific airlines. Again, this is a whether or not or true false problem. Production planning, specifically when you have like cars, laptops, physical entities, obviously you will have how many of each of the products should be produced. There are integers. Integer programming, we had linear programming, LP, now we have integer programming, IP. If we use IP or we use ILP, integer linear programming, or we have mixed integer linear programs, as you can see in the slide. If a linear programming problem has an additional constraint that requires the decision variables to have integer values, then it is called integer programming problem. In case only some of the decision variables required to be integer, then the problem is called mixed integer linear programming models. I'm adding linear because as a part of this module, we always have linear programming models until week 8 that we will cover some non-linear programs. So when we're talking about integer programming or mixed integer programming, we're talking about mixed integer or integer linear programs. So this additional constraint that we have here, the decision variable should be integer, and it is, as you can see, an additional constraint that we have. Now, looking at this example, consider that we have this simple problem in the first step, I assume that this is an LP. X and Y, X1 and X2, both of them are non-negative. As you can see, there is nothing written here that it should be integer. So this is essentially a linear programming model where we have the feasible region. Okay, this is the feasible region of this problem because we have non-negative constraints and we have only one constraint here. Okay, now we add this extra constraint that the decision variable should be integer. How do you think that the feasible region will change? This is the feasible region that we had for the LP. Now we added this constraint, additional constraint, that the decision variable should be non-negative and integer. This is the new feasible region that we have. It's only 6 points that we have. 1, 2, 3, 4, 5, 6. Now, I'll go to the points that I explained to you last week. Interpretation of solution, LP solution. What do you think if without this integrality of the decision variables, the objective function value was 25, let's say, if the LP gives us a solution which is 25 by adding integrality of the decision variables, what do you think how the objective function value will change? The LP, there is no constraint on integrality of the decision variables. We solved the problem, we got the solution, the optimal solution is 25. Now we solve the problem with integer values. As you can see, the feasible region is changed. Still, we can solve the problem. We solve the problem. What do you expect from the optimal solution? If the LP gives you 25, what do you expect from the integer problem? It will reduce. Why it is going to, what do you think that it should be reduced? Think about it and write your thought on the chat box. Decreasing optimal solution. Why? Give me the reason. I know in the next slide there is an example, so give me the reason. Remember the hint that I told you, I gave you when I was teaching you. The optimal solution might not lie on the binding constraints. Okay, it will not necessarily lie on the extreme points of the feasible region. Okay, do you remember? Do you remember that I explained you when we add a new constraint, when we remove the constraint? I gave the example with your life, with our lives. Do you remember that? When we have integrality of the decision variables, obviously we are adding some extra constraints to the problem. Do you remember? When we add new constraints to a problem, what do you expect from the problem? Do you expect to get a better solution or worse solution? This was the terminology that I was explaining. Remember from your life, I said, if you have a new constraint, if you have a new limitation in your life, do you expect your life to get better? It stays the same. It's not worse. You have a new, you're so rich and you have a new budget constraint. I mean, the thing is, your costs are below the new budget constraint that you have. Obviously, your life doesn't change, right? So when you have extra constraints and an extra limitation in the problem, you expect this solution to get either worse or stays the same. If the initial optimal solution is integer, it can stay integer as well. So this is what I'm trying to say. For this specific example, yes, it gets worse because the optimal solution of the LP is not integer itself. The new one should be integer. Therefore, the new solution will be worse. And worse for a maximization problem is a lower solution. Okay, great. So I said in this slide, you can see the optimal solution of the LP is 26.67. We solve the problem. We need to get integer solutions, and it is 0 and 3, and it gives us 24. We expected this because integrality of the decision variables means that we are adding some constraints to the problem. Adding new constraints or limitation to a problem means that we are making it harder to solve the problem. The optimal solution either stays the same or gets worse. Worse for maximization problem means a lower answer. Now, let's look at a very famous integer integer programming model. Knapsack problem. It is very famous. So if you just Google knapsack problem, you see lots of papers, research papers written by famous people how to solve it. A knapsack problem essentially is a problem that you have a knapsack. A knapsack backpack has limited capacity, right? And you want to decide, you want to go to for a hiking, and you have lots of stuff that you want to pick. The capacity of the knapsack that we have here is 60. You have 60 kilos, or volume-wise, or whatsoever is the unit of the knapsack. As I said, it can be kilo, it can be volume in terms of like liters, or anything else. You have a couple of items here that you can take with you when you're going on hiking. Each of them has a value for you. If you have these boots, you will wear a hiking boot, but you don't know how the weather will be, so it might be good to have a plan B if it is like snowing up there. Having this boot would be fantastic, and you can see it has a value of 12 for you. It is fantastic. You can have this light with you, this torch with you, but you can see that the value is 2 because you don't expect to stay there when it is dark. So if you take it with you, it is good just to be on the safe side, but you can see the value is not that big. You have this this gas fire, or whatsoever it is called. It is 7 because you may decide to have a coffee there. Your thermos here, this is also important. You have a helmet, glasses, so on and so forth. So there are different items that you have. Each of them has a value for you because you don't know what's going to happen there. If it is, for instance, you expect a cloudy day, so having the sunglasses is not something that you would benefit from. And for each of them, there is a size associated with them. The boot, it's massive. It takes like 1/3 of the backpack, but you can see the value is also very high. The torch, it is small. The size is small. The value is also small. Now, here, what you want to decide is which items should be taken, which ones not. The more items, the more combinations that you have. So here you have this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. You see different combinations that you have here to pick without violating the capacity, which is 60. You can take different items without violating this one. The more items that you have, it's the knapsack problem, but your knapsack might be a truck. In a truck, you have to decide different, there is a capacity associated with the truck in terms of volume and also in terms of mass. There are different items that you have for each of them. If you carry them, there is a value that you will earn, but the sizes are also different. So you have to decide which combination of items you have to take to maximize the value that you will get from this, right? So here we have to decide which items we have to pick, which ones we shouldn't. What do you think in terms of decision variables? Which sort of decision variables we have to have here? Which sort of decision variables we have to have here, and how many decision variables we have? Can you write it on the chat box for me, please? Yes or no? 10. Integer, great. 10, fantastic. 10 decision variables that we have. I have to decide boots. Yes or no to the boots. Should I take the boots or not? Torch, yes or no? Helmet, yes or no? Yes or no is true, false, 0, 1. Boolean decision variable that we have to introduce. Yes, you're right, it's integer. All Boolean decision variables are integer. Integer variables are continuous, but not the other way around. All continuous decision variables are not integer. All integer decision variables are not Boolean, but the other way around, it works. So we define the decision variables at xi if item I is in the knapsack, 0 otherwise. The terminology that we use here for the mathematical programming is that these decision variables, xi's, are binary decision variables. Boolean is for computer programming. Binary is for mathematical formulation. So it is, you can say, x in is in the set of either 0 or 1. It's not between 0 and 1 because we use curly bracket here. This means that it's either 0 or 1. So I guess I answered your question, Sebastian, that the terminology that we use here is binary. It's not integer, it's not Boolean, we use as binary. Or you can just show it with xi is in the set of 0 and 1. In computer programming and coding, we have true, false, or Boolean. In mathematical programming, we have binary or 0, 1. Our task here is to formulate an integer linear programming model to find a solution to the knapsack problem. X1 if item 1 is taken, otherwise it is 0. So when you're defining the decision variable, you have to define them in this way. In your model, you will write it x1 is in the set of 0 and 1. We want to maximize the values. Essentially, the value from the first item is 12. So 12 multiplied by x1. This means that, let me change the color. I don't want to, blue should be fine. So x1, if you take boot, the value which will be added to the objective function value essentially is 12. If you don't take it, it is 0. For the second one, 2 multiplied by x2. x2 is either 0 or 1, right? So if it is 1, the value becomes 2 will be added. What is the constraint that we have? How many constraints we have in this problem? Can you think of that? The objective function is obvious, right? Values multiplied by all decision variables, because if you take them, the value will be added to the objective function value, otherwise it is 0. One constraint that we have, apart from non-negativity or integrality or binary decision variables, the maximum capacity is 60. So the first one, if you take the first one, which is boot, the size is 20. So 20 multiplied by x1 plus 3 multiplied by torch x2, blah, blah, should be less than or equal to 60. So this is the constraint essentially that I'll have. Size of the first item multiplied by the decision variable, size of the second one multiplied by the decision variable, so on and so forth. It shouldn't be more than the capacity. That's the whole point. And we know all decision variables are binary. So this is the way that you write the model. This is the way that you define the decision variables. Do you think that it is an easy problem to solve? What do you think? Is it easy to solve this problem? Because we have only one constraint, and it's just the objective function. That is it an easy problem to solve? What do you think? No, that is super hard to solve the problem. That's why I told you there are loads of papers which are written on how we can solve this problem, because the combination of them is a lot. Yes, too many combinations that we have. You have 10 here, you can see. You can go with 1 by 1 items, 2, 2, 3 combinations, 4 combinations, 5 combinations. So it is not linearly, when you have the time it takes or the number of combinations is not linearly increasing, it's logarithmically increasing. So the more items that you have, the more combinations that you have, the more combinations that you have, the biggest solution space that you have. Therefore, it's not easy to solve this problem. Okay, any questions up to now? Good. This is up to you, that you decide how the decision variable should be. Forget about this for the group assignment. Again, read the brief carefully, and it is written that all decision variables should be linear, continuous. We want you to model them as linear programming. These are not linear programs because the decision variables are not continuous. Okay. What does the value play in our constraint? What does the value play in our constraint? What you mean? Value, you mean the value of the nothing. You don't have the values in the constraints. Values are in the objective function. Size is in the constraint. So there are different things that we have here. So in general, are there any other differences with the linear programming problems than type of? No, that's all. But the type of the decision variables that you introduce are also different. So let's have a look at this problem. Read the problem for a few minutes. I want you to think about the problem, and then think about the decision variables, and then I will explain to you the model. Let me read the model, the problem. So that's the written statement that we have. A textile company manufactures 3 types of clothing: shirts, shorts, and pants. Each week, 150 hours of labor and 160 square meters of cloth are available. Additional data is as follows. So here we know for each type of the products that we have. For shirt, how much labor we need, how much cloth we need, and what is the sales of the prices of these shirts, and what is the cost of producing these shirts. For shorts, again, we know how much labor, how much cloth we need. For pants also, we know how much labor, how much cloth we need. What are the prices for each of the products, and what are the cost of production for each of the products that we have. Formulate an IP which maximizes weekly profit. What do you think? What should be the decision variables of this problem? Think of the decision variables. How many decision variables we have? What are the types of these decision variables? We have 3 decision variables. Okay. What are the types of these decision variables? Continuous, binary, or integer? Integer. What are the decision variables that we want to have here? We want to decide how many shirts, how many shorts, how many pants we have to produce. This is very similar to paint problem, right? That's exactly the same that we have. In the paint problem, we had the prices. There was no cost that we had. We had 2 raw materials. We have labor and cloth here. We had 2 products. In the previous one, we have like 3 products here. Shirts, shorts, and pants. So we want to decide X1 and X2, X3, number of shirts to be produced, number of shorts to be produced, number of pants to be produced. The objective is to maximize weekly profit. Profit comes from revenue minus cost. So for each of the products that we have, for each of the shirts, we know the price is 16 and the cost per product is 8. So essentially, the profit of each of the shirts that we sell is 8, shorts 6, and pants are 9. Okay, that's good. How many different constraints we have in this problem? Think of the constraints. How many constraints we have? 2. Okay. 2. 3. Okay. We have 2 operational constraints, it's called. We always have non-negativity or integrality constraints. That's something that we have. So apart from them, we have 2 constraints to make sure that the availability of labor and cloth are respected. We don't want to, obviously, we want to respect them. So we have constraints on how much labor and cloth we have, and we have to respect them. Essentially, for a shirt, we know 3 hours of labor. For shorts, 2 hours. For pants, 6 hours we need. So in total, 3x1 plus 2x2 plus 6x3 should be less than or equal to the availability of labors, which is 150. The same we have for the cloth. The cloth shouldn't be more than 160. 4, 3 plus 4 should be less than or equal to 160. And finally, we have, oops, how did I do that? Okay, now let's see. So here, obviously, we have non-negativity constraint. Xi should be greater than or equal to 0 because you're not going to produce -2 shirts. Also, you have to make sure that all of them are integer decision variables. Now, we solve the problem. It's a maximization problem, and we have these 2 constraints. They are non-negative. Obviously, when we solve the problem, we get this solution, which is x1 equal to 0, x2 equal to 36, and we have to produce 13 pence as well. Okay, that's the a very easy problem to solve here, because maximization with respect to the utilization of the resources, it will be decided how many of each of them we have to produce. Okay, now we have some extra information here. It says that assume that the machinery for manufacturing each type of clothing must be rented at the following rates. Okay, it's not only the variable cost that we have. The variable cost of each of them was given. Right? These are the variable costs for each of the shirts, shorts, and pants. These are very product. There is a cost that we have to obviously pay. Electricity, water, and other stuff that we have. But now, apart from that, if you want to produce shirts, you have to rent this machine that you have to pay 200 per week. If you want to produce any shirt, you have to rent this machine, which costs 150 per week. And finally, pants, you have to pay £100 for the machine that you have here. Now you have to modify the IP model that we had. How we are going to modify the integer programming that we have here? What do you think? Oops. How we are going to modify them? We need to subtract the objective function because the objective function that we had here was only the net profit from production. Now we have extra cost that we have to add to the objective function. Yes, that makes sense. But first, we have to answer this question. Are we going to produce any shirt or not? Because if you're going to produce even one shirt, you have to pay this £200. Let me just erase the slide. Okay. Now, if you want to produce only one shirt, you have to give this 200. If you want to produce only one short, you have to rent the machine and you have to pay this much. If you're going to produce one pant, again you have to you have to rent the machine and you have to pay £100 apart from the variable cost that you have. So at the end of the day, you come to the fact that you have to produce as much as, at least a certain number of shirts, shorts, or pants that covers the fixed cost of the machines that you have here. Okay. We would encounter these values, W new constraints. Okay, first we will check whether all clothes are manufactured or not. You have to, not all of them, you have to decide on which products should be produced or not. So we have this question, yes or no. For each of the product types, we have to answer this question of yes or no. Should we produce shorts, shirts, or pants, or no? Because if you produce them, there is a cost associated with them. That's the whole point of optimizing. If there is a profit, if there is a cost, if there is any sort of something which impacts the objective that we have to make a decision about them. Okay. Now, to represent these decision variables, it's a binary decision variable or a Boolean one in terms of mathematical programming. We said that these are binary decision variables, yes or no decision variables. We introduced new decision variables, yi, because we had xi, which was the number of each item. Now we have yi, which is a binary decision variable, true or false, yes or no, essentially 1 or 0. 1 if we decide to produce product I, otherwise it is 0. We define them in this way. yi is 1 if shirts are manufactured, 0 otherwise. Y2 is 1 if shorts are manufactured, 0 otherwise. Y3 is equal to 1 if pants are manufactured, 0 otherwise. Now we have to modify the objective function first. Okay, but before that, what we have here is if you decide to produce any of these, so shirts are manufactured, shorts manufactured, means that, remember that x1 represents shirts, x2 number of shorts, and x3 pants. So if x1 is greater than 0, which means that we are going to produce shirts, then y1 should be equal to 1. This means that essentially you rented the machine so that you are able to produce any shirts. You rented the machine for shorts, then you can produce shorts, which means that x2 is positive. If x2 is positive, essentially you rented the machine, so y2 should be equal to 1. So here what we have, there is a relationship here that if xi is greater than 0, then yi should be equal to 1. Or if xi is equal to 0, which means that we are not producing that specific product, the associated void should be equal to 0. Well, you should produce it. Okay. Now, first I'm going to modify the objective function. This was the objective function that we had. This is the profit, right? This is the profit that we have, which is the revenue minus the cost. Okay. Now I'm going to, as someone said in the chat, erase all link. We're going to subtract the objective function from the weekly cost. 200 multiplied by y1, 150 multiplied by y2, 100 multiplied by y3. So if you're going to produce shirts, you have to rent the machine and you have to pay a one-off payment. This is the weekly profit. We're talking about weekly production plan. If you want to produce any shares on that week, you have to pay the rent for the week, which is 200. You pay it only once. And then you have these decision variables and constraints, and you solve the problem. When you solve this problem, it's a maximization problem, right? This is a maximization problem. y1, 2, 3 are in the objective function with a negative coefficient. When you solve the problem and there is nothing to limit y1, y2, y3 to become, there is nothing to force them to become 1. So when you solve the problem, added this one as well, the integrality of y1, y2, they are binary decision variables. When you solve this problem with this objective function, which is maximization of profit minus fixed cost of renting or rent cost, with these constraints, when you solve the problem, what you get here is a bit weird. X1 is still equal to 0, perfect. And we said that when x1 is equal to 0, you expect y1 to become equal to 0, right? That's sensible, because if you're not producing any shirts, well, you should rent a machine. So that's fantastic. When you look at shorts, that becomes weird. So x2, which is the number of shorts, it is 36, fantastic. But you expect when x2 is greater than 0, then y2 be equal to 1. But you can see from the model that we have, y2 is equal to 0. x3, again, it is positive. You expect y3 to become equal to 1, but it is equal to 0. This is because when you look at the objective function here, there is nothing to force y1, y2, and y3 to become 1 when x1 and x2, x3 are positive. That's why we got this weird solution. You go to the manager and you tell them, oh, you have to produce this one. This is the objective function value that we have, the profit, but then they ask you, oh, don't see any rent in the calculation that you gave me, which is weird. This is because the link between xi and yi is not added to the model that we have. It is missing here. The link between variables x and y are essentially missing here. You have to make sure that there is a link between them to make sure that if xi is positive, yi is equal to 1. Okay, we have to put them as a function, as a constraint. Remember, the constraints are always function in the left-hand side. Then you have less than or equality, greater than or equality to a number. Okay, we want to do the same. This is not a constraint, and you have it's written as if then. I want to make sure that I have a linear function written for these decision variables, xi's and yi's, to satisfy this constraint. When xi's are positive, then yi are equal to 1. Here is the slide. Okay, fantastic. This is what I have. Do you agree with this? When you have x1 less than or equal to y1, is this something that we can get? If it is positive, it becomes equal to 1. Is this something that we can see here? So this is what I wrote, right? When xi is positive, then yi should be equal to 1. Do you agree that we have the other way around as well? When yi is equal to 0, do you expect xi should be equal to 0 as well? When yi is equal to 0, this means that the machine is not rented. If the machine is not rented, how many of this product you can produce? 0 of them. Do you agree that it is satisfied now? When yi is equal to 0, do you agree that xi is also forced to become equal to 0? How about the other way around? I want to make sure that when yi is equal to 1, machine is rented. I want to make sure that I can produce a certain number of these products based on the other capacities that I have. Is it satisfied here, or there is any problem here? When yi is based on what I have, x1 less than or equal to y1, that's fantastic. When yi is equal to 0, then xi is equal to 0. It is forced to become equal to 0. But now I want to think of the other way as well. When yi is equal to 1, which means that the machine is rented, I want to be able to produce a certain number of products. It is not satisfied here because yi can be 0 or 1. So xi is essentially, x1 is essentially either less than or equal to 0 or less than or equal to 1. So the maximum that x1 that can get is equal to 1. This is not what I want. x1, x2, x3 should be able to get in bigger numbers. You may produce 20 or 36 that we can see here, 13 here. So that's why what we do is we multiply the right-hand side of this constraint by m. M is a large number. M is equal to 2, 0, 0, 0, 0, 0. It's a large number. Why it is this way? Because if I write it in this way, when y1 is equal to 0, then x1 is less than or equal to 0. I know x1 is greater than or equal to 0, therefore xi becomes equal to 0. When yi is equal to 1, x1 becomes less than or equal to m, which is a large number. Based on other capacity constraints, xi may get a value which can satisfy other capacity constraints. Obviously, it can be 2 million or 2 billion, right? Because we have capacity constraints on labels and clothes that we have. Do you agree that it works? If I have x1 less than or equal to m y1, when y1 is equal to 0, x1 is forced to become equal to 0. When y1 is equal to 1, then x1 can get an integer value based on other capacity constraints that we have. Okay, so this way, as you can see, when x1 is a positive value, you can see that y can get a value of 1, which satisfies this constraint. So my eventually my model becomes like this. Now, if we solve this model, we don't get the weird answer that we got from the previous one, x2 equal to 36 and y2 equal to 0. When x2 is equal to 36, y2 becomes equal to 1, and obviously the objective function value also, this max set changes because this 150 will be indeed subtracted from the objective function value that we found there. So when we solve the problem now, you can see that this is the true answer that we get. x1 is equal to 0, y1 is equal to 0. That's great. x2 is equal to 53, y2 is equal to 1. That's good. And finally, x3 equal to 0, y3 is also equal to 0. Okay? There is something here. As I said, m can get a very large number. Okay? But we don't want to use large values because we know that because of these two constraints that we have here. Okay. And because of these two constraints that we have, obviously x1 has a maximum that it can get. What is the maximum that x1 can get? Can you guess from these two constraints? What is the maximum that x1 can get? x1, the largest value that x1 can get is when x2 and x3 are equal to 0. When x2 and x3 are equal to 0, 3x1 is less than or equal to 150. x1 can be at most 50 from this one. How about the second one? This is equal to 0. This is equal to 0. 4x1 is less than or equal to 160. Therefore, x1 can be at most equal to 40. When you have different constraints, you have to focus on the tightest one. This gives you 50. This gives you 40. So the maximum value that x1 can get is equal to 40. So essentially this m for the first constraint is 40. So x1 is less than or equal to 40 y1. You don't need to use 1 million, 2 billion whatsoever. Okay? And when you solve this problem, you get the values that we got here. Great stuff. I'm very on time. I'm really happy with my timing. This was the last slide that I had. We'll work on similar problems in the workshop, so don't worry about it if it is a bit confusing. Work on them until the workshop. So when I ask you in the workshop, did you work on them? Don't just say no. Please work on them. Watch the video again, and it will be easier for you to follow the questions that we have in the workshops. Fantastic stuff. I'm not going to stop the recording for the question and answers. If you have anything else, feel free to leave. It's up to you. If you want to stay to ask question or just listen to the solutions to answers, stay. If you're leaving, fantastic. I will see you on Wednesday or Friday. Questions? Can you repeat this again? So let me erase them. So what I said here is repeat this. What you mean? Which part you want me to repeat? It's not the whole lecture, is it? No. Do you mean like M thing, or because I don't know when did you write it? Is it 40 and 50? Okay. I said there are two constraints that we have here, right? The first constraint towards the here. The first constraint gives you x1 less than or equal to 50. The second constraint gives you x1 less than or equal to 40. When you have both of them, x1 can be at most 40, because if you go with this 50, this constraint doesn't let you have x1 of greater than 40, right? This constraint doesn't allow you to have x1 greater than 40. This one, on the other hand, gives you 50. So the one which tightens more is the one that you have to consider. That's what I'm saying. Is it clear now? Could you repeat this again? Why we use M? Oh, why we use M is another thing. So if we go back to this one here, x1, essentially, I showed you that x1 can be at least 40, right? And this constraint here only is here because we want to have a link between x and y. There shouldn't be any extra limitation on what the value of x1 can be. The value of x1 comes from this two capacity constraints. This one only wants to build a bridge between x and y. That's why I said that this M should be a big number. x1 is less than, here I showed you that x1 from these two is less than or equal to 40, right? If I put it as x1 less than or equal to y1, y1 can get 0 and 1. This means that x1 is less than or equal to 1, but this is not what I want. Because I know from capacity constraint, x1 should be can be at most 40, but this is limiting x1 to be equal to 1. This is not what I want. I only want to build a relationship between x and y. That's why I said I multiply the right-hand side by a big number, m, which is 1,000,100 or 100,000 or whatsoever that it is. Okay, so that I know x1 is not limited by 1. So it is less than, let's say, 1,000 y1. When y1 is equal to 0, x1 is forced to become equal to 0. When y1 is equal to 1, now x1 can be any value less than or equal to 1,000. But I know, again, from this one that x1 can get a value of as big as 40 only. Okay? Does this make sense? I guess I answered your question, Manoj. Python question. In Python, it's exactly the same thing that we do. I'll show you an example on Monday, on Wednesday, and from the workshops. That instead of non-negative reals, you will have non-negative integers. That's all that you'll change. Are the rules on how to define M? as I said, you can have a big number, but a big number means that you will need more memory in your problem. We'll focus on this in the workshops. So 40 is the value that you have to use for m in the first constraint. So it means the value of x1 should satisfy both constraints. I guess you understood what I said. I'm not sure if I understand your comment here. So it means the value of x1 should satisfy both constraints. All constraints should be satisfied. You can't say that I won't satisfy this one. Can't we do like say greater than or equal 200? Is it the constraint you mean? Ronit, you said can't we like 8x1 greater than or equal to 200? So in this way, you mean that you're forcing x1 to get a positive value. What should you do? You may decide, as we say, when you solve the problem, we got the solution that x1 and x2 are not produced. Products 1 and 3 are not produced. But if you put them in this way, you're forcing all of them to be produced. It's not what we want. You may decide not to produce some of the products. If xi less than or equal to my1 represent the correlation between xi and y1, then how do we draw a constraint that says yi will have only values if xi does it not show that what I wrote? So you have xi less than or equal to let's say 40 y1. When y1 is equal to 0, x1 is forced to become equal to 0. When x1 is equal to 1, then y1 is forced to become equal to 0. Is it not the correlation that we are talking about? When y is equal to 0, x is forced to become equal to 0. Then you don't have the machine, you can't produce any. If you decided to produce any, then you have to rent a machine. So when x is equal to 1, y is also equal to 1. Did I answer your question, Oak? That's a very good question. When x is equal to 0, can y be equal to 1 mathematically? Yes, it can be, but you have this objective function, right? An objective function is to maximize something, and y is here with a negative coefficient. So it is always 0 by default, unless it is forced to become equal to 1. And it is forced to become equal to 1 when x is equal to 1. That's a fantastic question. Did you answer it? Did you get the answer? Can we solve this problem using graphical approach? No. We can't solve them. Why we can't use graphical approach? First, because we have 3 decision variables. Second, it's not linear programming. We said that only linear programming models are solvable with graphical solution method. Did I answer your question, Manoj? I didn't understand that at first, but I guess. Like as we selected x1 equal to 40, so it is satisfying first constraint. Still, I don't get what you mean. Like as we selected x1 equal to 40, so it is satisfying this first constraint. Okay. What I'm saying, x1, even though x1 can be, let's say 50 in the first constraint, this is not a solution because it doesn't satisfy the second constraint. All constraints should be satisfied. If you get this, don't worry to explain me what you mean. I'm okay with it if you understand what I mean. How do we force that? As Rn, it's like a logic that we need to input by ourselves. Yes. When you are referring to a previous question, please reply to that so that, because I can't remember what did you ask. If yes. This is something that you should understand from the problem. You have to build the relationship in your mind first, then you translate it to mathematical programming. That's what we do. Great stuff. Yo Yang, that you asked me this question about y being 1 when x is equal to 0. If you're in the first workshop of Wednesday, would be nice if you remind me of this so that I will explain it. Great stuff. Do you have any other questions? Will the value of m change the results of IT problems? No, IP problems. No, that's also a good question. I mean, if it is big enough, it is bigger than 40 in our case. No, it doesn't change this way, because if you have a tighter constraint, that will be essentially the one which force the feasible region. So if rather than 40 you use 40,000, there is no harm. But if wrongly, instead of 40 you put 30, that becomes a wrongly impactful constraint. Great. Any other questions? I didn't understand completely mixed integer program. What does it mean by it can have only some of the variables as integer? Sorry, I'm just trying to understand what you mean. You mean why some of them can be integer? Assume that you have a production line that you produce different products. Some of them should be integer, some of them not. So it's mixed integer. Even forget about that. Think of this problem that it's not shared shorts and pants. It's paint 1, paint 2, paint 3 with the same setting that we have here. Still, you have to rent some machines or something. The machines are there, so you will have binary decision variables, and then your x of 1, 2, 3 are continuous decision variables. This becomes mixed integer programs. Does the answer? Yeah. Okay. Great. Any other questions? So the numbers are down, and I'm going to stop recording. I'll see you in the workshop.